Okay, so I just got out of a meeting this morning where one of the topics of discussion was, how are we going to make math needs to be relevant. So in an effort to try to to do just that, you never know when you're going to find yourself in this situation in the land of logic. We got to know what to do. This could be a real world situation for you. So what do you do? I'm the guy. I'm standing at the crossroads. What do you ask me?
So my restriction is I can only ask you one question.
One question. Any simple question.
Are you a truth or a liar?
Okay, then if you ask me one question, I could say, oh, you don't know. You don't know what I am.
Yeah, no, I'm gonna ask you a truth or a liar.
Okay, so I'll say I'm a truth teller, is whatever, right?
Okay, then I'm gonna command you to walk me down the road of truth.
But that's not within your ability. You would be shunned. You don't want to be shunned. Being shunned is not a good thing. Yes, ma'am.
Can you ask him, like, if you're a liar, point to the city of lies?
Okay, now you're onto something there. You're kind of stepping around the boundaries, but you're very, very close. Follow that idea. Yes.
Could you ask them where the city of lies is, so that if they're a liar, they'll lie and say, oh, it's this way, but it's the city of truth. If they are
Okay, let's try that. So maybe I'm going to suggest maybe you could say point to the city of lies, something like that. Okay, so what if I point that way? If I'm a truth teller, what's that mean?
That's the right way.
Okay, what if I'm a liar?
That's the problem.
Okay, well, we're getting close. We're flirting with it here. Yeah. What can we do? There's a really elegant, simple solution to this. It's pretty cool.
Just trying to demonstrate what the state is, then what's wrong with it.
Well, okay, we're in a rush. When you know it, when you hear it, you're gonna think, oh my gosh. Okay. Well, I'm not gonna tell you. So I'm gonna let you guys think about it some more. We'll come back to it.
Divide yourself by two.
Divide yourself by two. Well, if the laws of physics were slightly different in the land of logic and quantum effects were macroscopic, then yeah, you would in fact do that for sure. But okay, so let's now. I think we left off yesterday. Weren't we talking about a question? Yeah. Okay. Let me pull that up. Okay, with these, let's take a look at this. We're given a piecewise function, and as I recall, you correct me if I'm wrong here, we had kind of talked about, reminded ourselves what that means to be a piecewise function. Yes, sir. One.
Can you just ask him where he lives?
Okay, back to that. Yes, in a sense, you can. Now let me slightly rephrase that. How about if you said, point where you live, right? Okay, that is going to work. Why is that going to work? Now let's imagine here, I'm at the crossroads, you're walking towards me. Let's say there's one fork goes this way and one fork goes this way. Let's just say, even though we don't know it yet, let's just say that the city of truth is out the door. Okay? Now imagine what my response is going to be. If you ask me where I live, if I'm a truth teller and you say, where do you live, where am I going to point? Okay, if I'm a liar, where am I going to point? So I always point to the city of truth. Very good. Isn't that cool? Yeah, how about that? So that's pretty, we don't know where he's from, nor do we know which city is which, but we can establish both. Well, actually, we can't establish both. We still don't know what he is, if he's a liar or a truth teller, but we know which city to go to. Good. So, try that one at home. See if your parents can get that one. Make them feel so. Okay, so I think what we said yesterday is we just kind of reminded ourselves what it means to be a piecewise function. So in terms of an ant's going to get dizzy walking on a piecewise function. He's going to be jumping from one behavior to the next as he crosses boundaries, right? For example, on this function, we said that was just a portion of a circle, right? If we did a graph of this real quick, it ends up being something like this, doesn't it? We're going to start at 0, so we got there's the first part. At 0, we're on this circle centered on the origin, kind of the top half of this circle, right? Walking to the right. When we get to 8, we're no longer on that circle. This is kind of small. Can everybody see that?
Yeah.
So notice that 8 is not included. So there's a hole in this first part of the function there. But at x equals 8, we are defined as being on this other function, right? So we're going to jump up to y equals 8, and we're going to walk along this horizontal line until we get out to 16. And when x equals 16, there's a hole in the function there, and we jump up to a y value of 16, right? So I guess that corresponds to this guy, right?
Yep.
Okay. Now, when we're trying to find the domain, and we're going to do a lot of this in calculus, and this is good pre-calc review. Finding the domain means we want to find the values of x for which this function is defined. In other words, what values of x would the ant be standing on firm ground? Okay? Well, what would that be?
0 to 16.
0 to 16. Yeah, for inclusive, right? So meaning we're going to include the endpoints. So there's a couple ways we could say that. If we used inequality notation, how would I say and write that? X is what?
Greater.
Okay, greater than or equal to
Oh, 0.
0 and
Less than or equal to 16.
less than or equal to 16. So there's one perfectly appropriate way of saying and writing that domain. A more compact version, and the version that we tend to favor in calculus, because it is a little more efficient, would be using interval notation, where we're going to use closed and open brackets and commas, and we're going to separate. Does that make sense? So now what's the difference between a closed bracket and an open bracket if we're describing intervals? Do you remember? Okay, one includes the endpoint and one does not. Which one takes more ink to draw, a square bracket or a rounded bracket? Square bracket. So that's the one that, I forgot to tell you this room's haunted. Yeah, I don't know, maybe some old mathematicians go. So if I do something wrong, you kick stuff off you'll know when I make a mistake. The square bracket takes more ink to draw, so that includes the endpoint. Okay, the rounded brackets use less, so they don't include the endpoint. Okay, so how would I say this interval then using interval notation? Close bracket, 0, comma, 16. Okay, now, and here's where there's a little bit of, you can go a couple different roads and they all mean the same thing. How do we say, what if I had to say something like all the values from 0 to 16 or the interval from 20 to 30? In Math Excel, they're going to want you to put a comma there, right? And then what if we said all values greater than 20 and less than or equal to 30? Then I would do something like that. Okay? That's how they're typically going to want you to do it. Another way of doing that, of saying or, is by using the cut, which is that. Oh, hang on. Yeah, that's right. Yeah, that's or. Yeah. Oh, is that or and? I can't remember now.
No, that's
That's right. Yeah, I think that's right. And so, they're going to favor the comma, but they mean the same thing. So you see a lot of these different, in math, there's slight variations on this theme all the way through. Yes, ma'am?
What's the upside down thumbs?
That's and. Yeah. So that's a conjunction. That means both have to be included. Or is a disjunction, means this or that. Okay. And we'll get into we're gonna get into some examples where we'll be faced with that situation here, soon. So you'll get some practice with that. Okay, so so the domain is pretty easy, right? We can look at this function and see from the collective domains where is the function defined. The range is a little harder. It's a little bit backwards because the range gets easier to establish after we have a bag of calculus tricks to analyze functions. The range gets a little bit easier, but for now we don't. And so honestly, the best answer for how do you identify the range is to look at a graph and see what the behavior is on a graph. You can kind of stare at it and think about it and do it that way, but there is no clear cut. It's not as easy as the domain. So based on our graph here, what is the range? What are the y values that the ant could walk on as he walks along the complete function here? Okay, let me erase this stuff. Okay, so shifting gears to range mode, and let's go ahead and just use interval notation. What would they be? What's the smallest y value the ant could have, or at least the lower limit of the ants? 0. Okay, does he ever stand on 0? So how do I start off my? Okay, good, like that. Up to what?
8.
Okay, and 8 is included. Good, but there's a gap, isn't there? Okay, gap. And then how do you do the 16? Now,
Like a weird.
okay, right. Now there's a couple ways you could do this. You could say there's in Math Excel, and I hate to throw this at you, but there are a number of ways in math that you could express this. The way I would do it, if I were teaching outside of Math Excel, I would just write down a 16. I mean, that's fine. That's another value of that's included. That's all by itself. In Math Excel, you use the script brackets to include a single point. Maybe you've seen that. Okay. There's another way that probably would also work in Math Excel, and that would be to say, I think you could probably do that also. You could probably say, you could probably do that. Did that work? Have you tried that? Anybody try that?
No.
Because it's that ought to work too if you use the square brackets because you're including that point 16. Okay. But I know that's the way I think
Is
that
that
they.
second one supposed to be square or round?
It's supposed to be square.
Okay.
Sorry, square. Okay. Does that make sense? So you literally, and the main point I'm trying to make here is that the range is best ascertained by looking at the graph. Okay. All right. And I did the email work? Did you get my little email?
Yeah.
Okay, good. Okay, so if you didn't, I pushed the date back one day so we could finish talking about this. All right, so let's talk about something a little bit new here today. I mean, it's not really new. What I'm going to do is I'm going to continue the discussion from, yes?
There's one more part to that problem. That's the
Oh,
part you didn't
whoops.
want.
Whoops. I'm trying to get off easy here. What's it say? Oh, yeah, the last part. Okay. I'm going to take a picture of this so it's a little bigger. Because this is actually a pretty important part.
Yeah, this is the part. This is the part. I never got it.
Alright, let's go. Okay, yes, determine those points C, if any, for which the limit exists. Okay, now, how many of those points are there going to be? Thank you. Okay. How many of those points are there going to be? And I'm going to go back. Gosh, I probably should have grabbed my picture. And let me do that. If I go there. Oh, it's darn it anyway. Gosh, I'm kind of stupid on that. Sometimes I don't think about this stuff. Let's see here. So let me quickly draw my picture. So wasn't it kind of, it'll be rough. It was kind of like this, right? Good enough? Okay. And this was 8, and that was 16. Okay. So on that graph, how many points are there for which the limit exists? Infinite number, right? Wouldn't it, in a way, be better to focus on the points where the limit doesn't exist? Yeah, and that's what we want to do. We want to figure out where doesn't the limit exist, and those are going to be the breaks in that set of values, right? Those are going to be sort of the, I don't want to use the word limit again, but those are going to be the endpoints of my intervals, right? So where doesn't the limit exist and why? Okay, at 0 it doesn't exist, for now at least, and why is that? Because you can't approach from both sides, good. So we can't include 0, that one's off limits.
Can't include 8.
Can't include 8, how come?
Can't approach it.
Okay, breaking the function, right, so 8 is off limits.
So is it 16?
and 16 is off limits. Now, why is 16 off limits? No, not a break in the function. Because you can't approach from both sides. Yeah. It would have been fine if this, what if we had kept going with this so it went out here like that? Then 16 would have been okay, wouldn't it? The limit would have been defined there, right? That works. Okay, but the reason it's not is because it's an endpoint. Okay, so then how do we say that interval if we want to exclude the endpoints of our interval and the interior point 8? Yeah, we'd have to just do this. 0 to 8 and 8 to 16 using rounded brackets, right? So all the values between 0 and 8 are okay, and all the values between 8 and 16 are okay. Make sense? Okay. Okay, so what I want to do now, I want to take a look at... Yeah, that's the answer, yeah. I want to take a look at... What did I do? I thought I grabbed the picture. Goodness. What's going on, Mr. Williams? Yeah, there it is. Squeeze theorem. Okay, let me put this in context a little bit. We've been talking about, remember we talked initially about evaluating limits graphically and numerically that first day, right? Kind of used, that's where we introduced the AND example. And for the last day and a half or so, we've been talking about the third option, which is not by staring at a graph or trying values, numerical values in a calculator or on a spreadsheet or something that just approach a value to see what the trend is. We're doing it sort of mathematically, analytically. And we've looked at a bunch of different cases where we have found ways to algebraically manipulate a limit to coax out an answer. And those were the types, when we initially tried to evaluate a limit, we said we get 3 possible outcomes. The first one, the easiest one probably was what? Real number, done. That's the limit. Second one was, okay, not a real number, meaning we had a real number divided by 0. And what did that tell us? No limit. Graphically it meant vertical asymptote. And then the third kind was sort of where we're going to spend most of the time, because that's where we got to do some algebra. The third kind was the more work kind, where we get an indeterminate form, 0 over 0, right? And we looked at some ways we looked at a couple examples of different types of problems and how we would approach those. And, I love doing those things, so, I love doing math, so I'm tempted to do more, but I'm not going to. You got an assignment to work on those, and, we'll come back and answer questions if we need to. What I want to do today is I want to extend that discussion into another type of indeterminate limit. And that would be a limit involving some trig functions that when we try to directly evaluate gives us a 0 over 0 answer. How do we deal with that? This is really cool. This is the proof that we're going to end up doing. It is, I think, a really cool proof because it's geometric. I mean, you can look at this thing and you can look at the trend of this proof, and it's all just geometry stuff. You're going to like it. But before we can do this cool proof, we need to know a theorem in calculus that we use called the squeeze theorem or the pinch theorem. And here's all it is. It's very simple. All it says is if we've got 3 functions, say we've got, let's call the green one g of x, and the red one we'll call h of x. Whoops, gotta make that red. And the blue one we're going to call f of x. Now, if locally speaking, so relative to some point c on the x-axis, locally speaking, so in the vicinity of C, in math we literally say in the neighborhood of C. And we don't care what happens way out there in that direction or way out there in that direction. But locally speaking, if f of x is always pinched between g of x and h of x, so g of x acts like a ceiling function and h of x acts like a floor function. In other words, locally speaking, if we had to say this in terms of an inequality, we would say that f of x is always greater than or equal to h of x and less than or equal to g of x. Then if at some point c, the the ceiling function and floor function, their limits converge on a single point, a single y value, what must happen to the pinched function?
Same thing.
Same thing, right? Does that make sense? If the limit of g of x as x approaches c is some value L, and the limit of h of x as x approaches c is also L, then definitely the limit of f of x as x approaches c has to be L, because it's pinched in between those two, right? Does that make sense? It's a very visual theorem, and it just makes sense. Okay, so what we want to do then is we want to look at a particular example here. We want to look at the example, what happens when we try to do the limit of sine theta over theta as theta approaches 0. You know, if we try to evaluate that directly, what do we get? What's the sine of 0? 0, right? Yeah. So we get 0 over 0, more work, right? Okay, now, you might be thinking, and I wouldn't blame you if you were, well, why are we focusing on just this one little example? Well, because this one, we get a lot of mileage out of this one little indeterminate form. With trig stuff, if you are adept, as I know you all are, at manipulating trig expressions with your trig identities, you can make just about every indeterminate trig form boil down to that one case, all right? And we'll get some practice. You'll see that you might be skeptical, but I'll show you. We'll look at some examples, and you'll see that with a little bit of finesse, we can make them all that pop out of all those, okay? So just like in the examples we looked at yesterday, for example, you know, if we factored things, we always found that there were those offending factors that would cancel. This is the equivalent, the trig equivalent of factoring out those, or canceling those offending factors, the factors that made the 0 over 0 happen in the first place. Okay, so how do we do that? Well, here's our cool proof, our cool geometrical proof. Let's just look at a circle, and let's take this angle right here to be theta. Now, if I extend this ray out that defines the angle indefinitely, I can define lots of things, but I can define 3 distinct areas, and let's separate those. We're going to color code those. We've got, let's call this our green area, is going to be this interior triangle. Okay? Our blue area is going to be this sector of the circle. Does that make sense? So is that bigger or smaller than the triangle? Bigger, right? Does everybody see what I'm saying when I mean this little triangle? I mean this, and I'll erase these in a second, but just so we can make sure everybody's on the right track. I mean this triangle. There's this small right triangle. Okay? Okay, here's the sector. So a piece of pizza. Right? And then the other area would be, we'll call it the red area, is going to be this large right triangle. Okay, so this one, if I draw the whole thing. Okay, we see it? So which is the, we'll call them green area, blue area, red area for now. Smallest is? Blue is middle, red is the big, right? Okay, so let's try to figure out what those are. Well, we can't tell what they are concretely because, of course, they can vary. We never pin down what theta is, but in terms of theta, we can actually define all these areas. What's the area of this green triangle in terms of theta? Now, what do we know? Oh, by the way, one other thing I got to tell you is that I failed to mention, this is really important. This is a unit circle. So the radius is 1. That's important. So if we focus on that green triangle, And let me redraw the green triangle down here maybe. What do we know about that green triangle?
The hypotenuse is 1.
Okay, hypotenuse is 1. Good. Okay. Now if we're trying to establish the area of a triangle, I guess we got to remind ourselves, how do we calculate the area of a triangle?
Base times height.
Oh, okay, half base times height. So, well, how are we going to do that? Well, we don't know. We don't really know what the angle is. Could be anything. Could be anything. What's the base of that thing? If this is theta, think about that for a second. Oh, you know what? Actually, hang on a second. You know what? I can make this a little bit easier. This would be better. Hang on. I got a better way to do this. Better way to do this. Let's make the small triangle. All that has to be true is it has to be smaller than the blue sector. That's a lot smaller, but wouldn't you agree that if I do this, I can pick another triangle that's a little bit easier to define an area for, that isn't a right triangle. It just looks like this. That's slightly smaller than the blue triangle, isn't it? Right? That's going to be a little bit easier. A little bit easier because now I'm going to keep this, I'm going to keep that in there because that represents the height of the triangle. Right? But, whoops. But now, there's our triangle. So that helps a little bit because now what's the base? 1. Okay, good. So we just need the height. We just need the height, and this represents the height, this dashed line. Oh, okay. Oh, sine theta. That's it, right? Sine theta, because this height, if I look at this little right triangle here, right, let's just focus on that for a second. We know that sine theta equals the ratio of opposite over hypotenuse, right? So if I focus on this little right triangle in there, that's 1, that's h, right? We know, and that's theta. We know that the ratio of sine theta is h over 1. So numerically speaking, in terms of a number, the height is sine theta, isn't it? Right? In other words, we could identify the coordinates of that point right there as being sine what's that going to be? Well, that'd be confusing. It'd actually be over cosine theta and up sine theta. But what we want to know is that that's just sine theta, that y value, right? Okay. So the green area is, and let's keep track of these, we'll call it A1, is just sine theta. Okay? Let's move over to the blue area. Everybody okay with that? Questions on that?
You completely lost me.
Okay, let's reverse course here just a little bit. We want to find the area of this triangle, right?
Okay.
Now we know that the area of a triangle is 1/2. Actually, the area is sine theta over 2, isn't it? Sorry, my mistake. It's 1/2 base times height. The base is 1. We need to know what the height is, though, right? So to find the height of the whole green triangle, let's just focus on that right triangle, okay, whose height is the same, right? If we focus on the right triangle, and it's kind of hard to see, let me draw it more solidly up here. How about? Here's our right triangle. Well, we know that the hypotenuse is 1, and we're looking for the height. But I know that that angle is theta, right? Now, what's the trig function that involves the known side and the unknown side? That'd be sine, right? Because that's relative to the angle theta, that's the opposite side in the hypotenuse, right? So we know that sine theta equals the ratio of opposite over hypotenuse. So if I solve for h equals sine theta, right? And so then the total area is going to be 1/2 the base, which is 1. Let me write that out. How about? So A1 equals, yeah, right, I forgot the 1/2.
Okay.
Equals 1/2 times the base times the height, right? which is just going to end up being, sine theta over 2, right?
Alright.
Okay, so there's A1. Let's find A2. Okay, now A2 is that blue sector, right? Does anybody know what the area of a sector is? Because I'm going to tell you a way to do this, a way to find this, a way to remember this, so you'll never forget it again, if you ever knew it and forgot it. If I want to find the area of a sector, and this is angle theta, how could I do that? No. Think about it, and this is supposed to be round. It's a piece of pizza. What's the area of a circle? Oh, okay, pi r squared. Okay, so, how could I do that? So this is really just a fraction of the area of a circle, isn't it? Right? So I want you to come up with this then. If I want to find the fraction of the area of a circle, well, what fraction of the whole circle is it? Theta. Okay, theta is the angle. What would the angle of the whole pizza be? Okay, but we want to work in radians, so that would be 2 pi. Okay, so wouldn't you agree that this is just equivalent? Is that us? Oh my gosh. I'll tell you what, I had in McMinnville, we had calculus for 70 minutes, and it was awesome. Because by the time you get rolling, we got to stop.